begin with the system of linear equations. So the definition is a set of linear equations in n unknowns. The unknowns are x1, x2, x3 up to xn, as given below, is called a system of linear equations. So there are n equations with n unknowns, and the coefficients of each unknown is aij, a11 x1, a12 x2, a1n xn. Then the second row, a21 x1, a22 x2, a2n xn equal to b2, and so on, an1 x1, an2 x2, and so on up to ann xn is equal to bn. So aij are the real coefficients of the unknowns, and b1 bi, that is b1 to bn, are real constants. So the solution of the system of linear equations is the set of values of x1, x2, x3, so on up to xn, which satisfies each and every equation of the system. Then only we call it as a solution. The set of values should satisfy every equation, otherwise we don't call it as the solution. So if the system of linear equations has a solution, then we say it is a consistent system. If it does not have a solution, we say it is an inconsistent system. If it has if it's a consistent system, then there are two categories. If it has a unique solution, then we call the system as determinate. And if it has more than one solution or infinite solutions, we call it as an indeterminate system. Now, the system of equations, the system of linear equations, can be called as homogeneous or non-homogeneous. Now, when is it called homogeneous system? It is called a homogeneous system when all the constants b1 to bn are zeros. b1 equal to 0, b2 equal to 0, b3 equal to 0, and bn equal to 0. And yesterday I explained why are they called as homogeneous. Because in each and every equation, every term of the equation has degree 1, is of degree 1. So therefore it's a homogeneous equation. Now if the variables are of degree 2, then it's called as a quadratic equation. If the highest degree of the variable is 3, then it is called as a cubic equation, and so on. So, but we are discussing with the linear equations, and linear equations by far is the most important in linear algebra. That is what we are discussing. So now let us go to the methods of solution of differential equation. So today's topic is the solution to the system of linear equations, and the most important of all methods is the first type. I will use Cramer's rule using determinants. Then we'll go to the other methods, the matrix inversion method. Now, Cramer's rule. We'll start with a system of equations with two unknowns. With two unknown variables. So we have A11 x1 plus A12 x2 is equal to B1. A21 x1 plus A22 x2 is equal to B2. Now I'm going by unknown variables, and I have explained this in the previous class. All right. In one of the previous classes, I have explained that how do you solve this? Okay. Suppose we are solving for x1. So what happens when we solve for x1? So what do? We multiply with, so we have to eliminate x2. So for that, what do? Multiply the first equation by the coefficient of x2 and multiply the second equation with coefficient of x2. Okay. Then what do we get? We get the coefficients of x2 now will become equal. A12, A22 times x2, then A12 into A22 times x2. So now we can subtract this. When we subtract the first term, we get A11 into A22 minus A1 or A21 into A12 times x1 plus 0 is equal to B1 A22 minus B2 A12. All right. So now we get x1 as B1 A22 minus B2. I will, before I go into this step, I will write this differently because I have to explain Cramer's rule here. This is this determinant of the coefficients A11, A12, A21, A22 times x1, and this one is determinant of B1, B2, A12, A22. Just observe. This one is the determinant of the coefficients A11, A12, A21, A22. This is the coefficients of the unknown variables. Whereas this determinant is obtained by replacing the coefficients of x1, that is A11 and A21, by the corresponding constants B1 and B2. So in this particular determinant, we replace the coefficients of x1 by the constants. So we will write this as delta, or sometimes you can write D, capital D for determinant. So delta into x1 is delta 1. All right. So that's what we get here. So where delta is A11, A12, A21, A22, and delta 1 is, you see, replace the first column of delta by the constants. Okay. Now next, this was solving for x1. Now let us solve for x2 in a similar way. So solving for x2, this I write this as equation 1. Okay. Now solving for x2, what we get is we have to eliminate the coefficients of x1. So we multiply the first equation by the coefficient of x1 in the second equation, and multiply the second equation with the coefficient of x1 in the first equation, and then subtract. Then we get a21 a12 minus a11 a22 times x2 is equal to a21 b1 minus a11 b2. Now just to keep the same determinant as in equation 1, we multiply with a negative sign throughout, both sides with a negative sign. This means a11 a22 minus a21 a12 times x2 is equal to a11 b2 minus a21 b1. This side, the left side, is determinant of a11 a12 a21 a22 times x2 is equal to determinant of, now a11 a21 remain as it is. You have to replace the coefficients of x2 in the equation by the constants. That's it. So this is delta or capital D, and this is delta 2 or capital D2. So this is our second equation. So now we will study these two equations very carefully. So our solution has boiled down to two equations. Delta into x is delta 1. Delta into x1 is delta 1. Delta into x2 is delta 2. This is the first equation. This is the second equation. Now we get three cases. Three cases. Case 1. Pay very careful attention. If delta is not equal to 0, that means the determinant is not equal to 0. The determinant of the coefficients of the unknowns, it is not equal to 0. Then what happens? If delta is not equal to 0, then we get x1 is delta 1 upon delta, and x2 will be delta 2 upon delta. So it's a division by a non-zero entity. So you will get some finite values of x1 and x2. Okay. So we get the solution we get is unique, or we say that, very important, listen very carefully now. The system has a unique solution, and we call that, therefore the system is consistent because it has a solution, and determinate because it has a unique solution. All right, very important. The system is consistent and determinate. Consistent and determinate. It's a consistent and a determinate system. Let us look at case 2. If delta is equal to 0 and delta 1 equal to delta 2 is equal to 0. So what are you getting? Look at our equations here. Delta into x1 is equal to delta 1. Delta into x2 is equal to delta 2. So what we get is, so you get, see, delta into x1 is equal to delta 1. This gives 0 into x1 is equal to 0. And delta into x2 is equal to delta 2. This implies 0 into x2 is equal to 0. Right? So this is our equation 1. This is our equation 2 now. What are the values of x that will satisfy the first equation, x1? There are infinite possibilities. Isn't it? Any value of x1, real value of x1, 0 into x1 will give you 0. So all the real values of x1 will satisfy this. All the real values of x2 will satisfy this. So we get here that x1 and x2 can take infinite values to satisfy 1 and 2. Therefore, the system, we say, has infinitely many solutions. The system has infinitely many solutions. We say the system is, what will we call the system as in terms of consistency and determinacy? Anyone?
Consistent indeterminate system.
Very good. The system is consistent and indeterminate. It's a consistent system, but an indeterminate system. It has infinitely many solutions. All right, the last case. Case 3. Now, if delta is equal to 0 and at least one of delta 1 or delta 2 not equal to 0. Okay, I would say, yeah. Then what happens? This is interesting. So we have delta into x1 is delta 1, delta into x2 is equal to delta 2. Let us say in a particular case, both are not zeros. Delta 1 and delta 2 both are not zeros. So we get 0 into x1 is equal to a non-zero quantity. 0 into x2 is a non-zero quantity. Is it possible to have x1 and x2? Is it possible? 0 into some real number is a non-zero quantity. Is it possible? No.
No.
So x1 and x2 have no real solution. They don't have a real solution. So the system has no solution. The system has no solution. The system is called as inconsistent. The system is an inconsistent system. Clear? These three cases, you get a real solution, unique solution, if the delta, the determinant of the coefficients, is non-zero. Determinant of the coefficients of the unknowns, if it is not zero, you get a unique solution. So system is consistent and determinate. You can get many solutions if the determinant of the coefficients is zero, and in addition, these determinants delta 1 and delta 2, there are also zeros. Okay, then the system is consistent and indeterminate. It has infinitely many solutions. Then last one, if determinant of the coefficients is zero, but at least one of the other determinants is non-zero, then the system has no solution. It is an inconsistent system.